Example number 2 for simple harmonic motion, we have at time t equals 0, the displacement at time 0 of the block in a linear oscillator is negative 8.5 centimeters. So our displacement at time 0 is a negative 0.085 meters. And the block's velocity at time 0 is negative 0.92 meters per second. And its acceleration at time 0 is 47 meters per second squared. A, what is the angular frequency of the system? And B, what are the phase constant and amplitude? So for part A, this problem is a hard problem. And the reason for this is we don't have enough information to really get the angular frequency in an easy way. So we know that it is a block on a spring. Well, it says a block in a linear oscillator, and I'm sure the figure is a block on a spring. But they don't give us the mass of the block. They don't give us the spring constant K of the spring. So, and they also don't just give us the amplitude. So it's not particularly easy to find angular frequency. However, what we can do is we can use our equations for displacement, velocity, and acceleration, and actually divide the equations by other equations in order to actually get our angular frequency. And I'll show you what I mean by that. So we know our displacement equation is displacement as a function of time is equal to the maximum position times cosine of the phase, which is omega times t, plus the phase constant. Now here, if I'm talking about the displacement at time t equals 0, I can plug in a 0 for my time in my phase. So I get displacement at time 0 is equal to x maximum cosine of just phase constant, because t is equal to 0. Now we can do the same thing with the velocity equation. So that's negative omega times x max times the sine of the phase constant. And then also with acceleration, we get negative omega squared times x max cosine, not sine, phase constant. Okay. Now for part A, we want to know the angular velocity. Now what we're going to do here is we're actually going to divide the acceleration equation at time 0 by the position equation at time 0, because they both have cosine in them, so we can get rid of that cosine of the phase constant term, and they also both have the amplitude in them, so we can get rid of that maximum x position term. So we get negative omega squared xm cosine of v. And then we get x maximum cosine v. So we're dividing these two things. So what we end up doing here, we get to cancel out cosine of the phase constant and also that amplitude. And so what we end up getting here is just the acceleration at time 0, which was 47 meters per second squared, divided by the position at time t equals 0, which is a negative 0.085 meters. And that is going to equal a negative angular velocity squared. So negatives cancel out. We take the square root here. Angular velocity is going to be equal to 47 meters per second squared divided by 0.085 meters. And so we get 47 divided by 0.085, and then take the square root of that, and we get that the angular velocity is 23.5 radians per second. All right, so that is letter A. And then for letter B, we're going to use the same method, but it is even more complicated, which you'll see. So letter B, what are the phase constant V and amplitude X sub M? So we're going to do the same thing with the phase constant. Now, since we don't know what the amplitude is yet, we want to cancel out the amplitude. But we do know what the angular frequency is now from part A, so we can leave in angular frequency. So what we're going to do for this one is we're going to divide the velocity equation at time t equals 0 by the position equation at time t equals 0, because we want to leave some cosine sine of the angle of the phase constant in so we can find what that phase constant is. So velocity equation, we get a negative omega times x max times the sine of the phase constant. Position, we get a just x max times a cosine of phase constant. We're dividing these things. Now, again, our amplitude, x max, that cancels out. And then I know that sine divided by cosine of the same thing is tangent. So what we end up getting here is velocity, which was a negative 0.92 meters per second, divided by the position, negative 0.085 meters, equals a negative omega, which was 23.5 radians per second, times the tangent of our phase constant. So we get 0.92 divided by 0.085, and then I'm going to divide that number by a negative 23.5. So we get a negative 0.461-ish equals a tangent of the phase constant. Take the inverse tangent of this, and we get phase constant is equal to a negative 24.73-ish. Now I use degrees here. My calculator's in degrees. You can do either degrees or radians. It doesn't really matter here. But the key here is that this phase constant, doing this in terms of tangent here, we actually get two answers. So we get this, and we also get this plus 180. So we have two answers here. So if I add 180, we also get, 155.27. And so what we have to do here is we have to see which one of these gives us a positive x sub m. So we have to plug in to our our position function, in order to see which gives us a positive xm. And the reason that we need a positive amplitude is because if we look at the cosine graph, it starts up here. Okay, so in order to have a positive amplitude starting point, that phase constant has to give us a positive amplitude in that equation. Okay, so that's the key there. All right, so if we look at our position function, we get position, and again, I'm going to look at the position function at time t equals 0 because I know what that is equal to. That's going to be equal to xm times the cosine, again, of just phi, because it's cosine of the phase, which is omega times t plus our phase constant, but t here is equal to 0. If I solve for my xm here, my maximum amplitude position, I get x of 0, position at time 0, is equal to cosine of the phase angle. So plugging in my numbers here for both of my angles, I get xm equals my position at time t equals 0, that was a negative 0.085 meters, divided by cosine of a negative 24.73 degrees. And again, as long as my calculator is still in degrees, this is totally fine that you leave your calculator in degrees for this problem. If you got your previous answer in radians for your phase constant, just make sure that your calculator's in radians when you're doing this part as well. So we get negative 0.085 divided by cosine of a negative 24.73. And here we get negative 0.094 meters. Now let's do the same thing with our other angle. So we're adding 180 degrees to the angle. So we get 0.085 meters divided by cosine of 155.27. So we get negative 0.085 divided by cosine of 155.27, and we get a positive 0.094 meters. So what that tells me is that the 155.27 degrees is my phase constant, not the negative number that I got previously. So phase constant is equal to 155.27 degrees. You can also convert this into radians by multiplying by 2 pi and then dividing by 360. We get 2.7 radians for that. And then our x maximum, or amplitude, is equal to 0.094 meters, which was our other part of part